Assalamu alaikum. This will be the last chapter of this course. I'll try. This will cover the distance protection principle. I've covered in the previous chapters the overcurrent principle, the directional principle protections, and differential protection. And this I should know, why do we need distance protection if we have other types of protections? What's the working principles of this types of protection? What are the types of distance relays? They can work on non-bilateral when we have no communication between these types of distance relays, or when we have a communication between them. We call them pilot distance, or sometimes we call it communication assisted protection, distance protection. Where can we apply these types of relays? We can apply them widely as a primary and backup protection on the transmission and sub-transmission systems. Mostly for transmission, this is the primary protection, which is used to protect transmission lines. We don't use them in the distribution because in distribution, these types of relay are expensive, and distribution systems are mostly radial. We don't need these types of relays for distribution system. In generators, it's also used in the generator as a backup protection for faults in the systems. It's also used as a concept on loss of excitation, okay, in a generator also. But in this course, I'll cover the application of distance relay to protect transmission lines. Okay. What are the advantages of this type of protection as compared to like the overcurrent? So it provides fast operation, instantaneous for most of the line, from 80 to 90%. If a fault occurs in the transmission line, within 80 to 90% of that line, that fault will be cleared instantaneously. So that's comparable to the instantaneous overcurrent relay. However, the reach here almost constant as compared to the reach of the overcurrent can change. Greater sensitivity. You know, in overcurrent relay, we need to set the pickup setting of minimum 1.5 times the full load current, while here the setting is different. I set a distance, an impedance, okay, rather than based on current. So the measured impedance is independent of the current. The impedance values is see you later the principles. Virtually independent fault current level. So while operation over current depends on the current level. Okay. Easier setting as easier settings and calculations. So there is no need. The issues of coordination is especially when you have ring systems, and overcurrent becomes very complex. So it's much easier, okay, to set distance relays as compared to overcurrent relays. Fixed zones of protections, relatively independent of system changes. And as an overcurrent, the operating time can change as current change, although the fault location is at the same fault point. This is, I have covered this in the differential relay chapter. Like this is like a fixed zones. The zone, if it's covers 80%, almost covers 80%. There is a you know, a degree of tolerance or for these zone reach. to provide backup protection for adjacent line. This is very important. Okay, and differential, although it provide fast and instantaneous operation for faults within the differential relay zone, it does not provide any backup for adjacent elements, while this can provide as a backup. Its working principle? Its working principle based on the measurement of the positive sequence impedance between the relay location to the fault points. This is the basic principle. It's try to measure the positive impedance of the line and see if the and it decides whether there is a fault within the line or outside the line based on this measured impedance. If the impedance greater than, if the measured impedance, positive impedance, greater than the line impedance or a setting, then the fault is declared outside. If it is less than, the fault is declared as inside the line, and relay takes an action. And then this principle will assume that the impedance of the line is fairly constant, whether it's the parameters distribute the line parameters is transmission line parameter is fairly distributed along the line. Trips of the trips of measured impedance, as I said, less than a threshold value. So mostly if we have different zones, each zone has a setting. I will present this inshallah in the following slides. So it can measure the impedance, it can measure the reactance, it can measure the resistance, okay, of the fault impedance, okay, irrespective of the conditions I have. I'll just compare here, as I mentioned, the overcurrent, instantaneous overcurrent also provide instantaneous action. Now, if we compare the instantaneous action of overcurrent relays, there are some situations where we cannot provide instantaneous actions. And one of them is when we have no fault is here and fault is here is very close to each other. Remote fault current and local fault current are close to each other, then we cannot provide instantaneous here. And so there has to be a margin between a local fault and a remote fault currents magnitudes. There's another scenario, difficulties with an overcurrent, an instantaneous overcurrent relay. For this situation, which is shown here, I have two in-feed, okay, for this line, two sources that feeds this line. And now if I want to calculate the remote fault, okay, the remote fault current, I will find it by, and when these two sources are in service, okay, and when they are out of service. So for at F1, if we have 10 parallel with 10, the equivalent will be 5 ohm plus 4, it will be 9 ohm. So if I take the voltage 115 over √3 phase voltage over this impedance from the source to the fault point, gives me the fault current. This is three-phase fault current. So our pickups, if this is an instantaneous, the criteria, this pickup setting has to be greater than the remote fault current, has to be greater than this value. Okay, and normally I take this, say 1.25 greater, okay, than this. Now, for a local fault, if a fault occurs close to the relay, roughly at the bus or just after the bus, just here, okay, And so what will be the fault current? And one of them is in service, the other is out of service. This is the configuration, and a fourth almost at this bus, close to the relay. So the current will be the same voltage, phase voltage divided by the impedance, which is 10 now, because 4 is very close to this bus. So divided by 10, so there is a bracket here. And that will give this current. So the fault cannot be, the instantaneous setting cannot be higher than the local fault. If it is higher, then it will not detect any faults. If the settings here instantly greater than this value, it means it won't detect this fault. So we wanted to make it smaller than this value. So there is a contradiction now. I want it to be greater than this, so that if a fault at remote will not be detected instantaneously. A fault in the line, I don't want this to trip. Okay, so that I want to have current higher than this, so that which corresponds for somewhere here. But at the same time, it has to be less than this. So I cannot. This is one case that instantaneous overcurrent relay is not feasible to apply. So so what's the solution? Now I can have a distance relay, which is independent of this. Its operation almost independent of the source impedance. Okay, this, as you can see, the source impedance has affected the operation or the suitability or application of the instantaneous overcurrent relay. Now, how do we distance relay is applied? We need two inputs. Okay, one is the current from a CT and a voltage from a VT. Okay, and based on this voltage and current, I want to measure the impedance from the relay point, which is this relay location, to the fault point, based on this two measurements. So by Ohm's law, if we divide this by this, it gives me the impedance. Okay, it's measured impedance. And I would compare this impedance with the line impedance. Okay, so this represents the source impedance, which is all impedances behind the relay, and this is called the protected line impedance. So this relay is intended to protect this line. So this is my zone of protection. Okay. The impedance that I would measure depends, on the fault location. So if the fault's here at 50%, you will measure 50% here. So it's something. So the fault at the 50%, this is the line characteristic. So this is a point. Let's say this is bus A, and this is bus B, and this is Z line. So this is bus A location, which is this is XR plane, or we call it impedance plane or XR plane, and this is point B. Okay, the remote bus. This is the local bus. This is where relay location. Now to measure this impedance, if the fault is at the middle, it will measure half of the impedance. Okay, but because of a resistance here, I might have a fault with a resistance RF. The fault impedance can drift from the line impedance. So because of this resistance, I will measure 50% of ZL, if this is the fault at the 50%, plus a resistance in the horizontally, that could represent the RF. So let's say, so from here to here, so the impedance from here to here is the 50%. So impedance here to here, 50%, and so it is 0.5 of ZL plus this ZF. So that's 0.5 of ZL which is this value, plus this one RF. That gives me this apparent impedance seen by the relay. Relay will see this. This is Z measured by relay. Okay. Now, if I have a source feeding from this side, feeding also current, and this current from this source, this voltage across this RF will not be in phase, okay, and it might drift. So it will be like this voltage here. So you would end up with something at this point. This will drift up or down, depends on the amount of current or angle of this current that flows here. So the relay will see this not as a resistance; they will see it as inductance, or okay, plus resistance. So it is something like R plus this Y axis. So as a result, we cannot, the fault impedance will be, or this measured impedance can drift from here. So we cannot have a straight line, a setting which is equal to just a magnitude. So this is how the relay will see the fault impedance, the measured impedance. Now suppose this is the fault, the source impedance, the line impedance, and the load impedance, which is the load is connected to after point P. So this is bus P. And this is bus A, where the relay located. Now I have, as I said, we have voltage measurement from VT. We have current measurement that flow here, current measurement, but this is referred to secondary side. Now if you divide V over R, the value will be ZL plus Z load, right? Now when you have a fault occurs somewhere in the line, and the impedance of the line from here, from point A, where the fault location, to the fault point F in the line, this impedance we call it ZF. Okay, this ZF could be 50% of Z line, could be at 80%, anywhere, okay, in the line. So when there is a short circuit, three-phase short circuits at point F, now the impedance that will be measured by a relay is ZF, and ZF here is less than Z line, okay? And as a result, we can declare this relay can declare the fault is in the line. Now, instead of comparing with ZL, the relay compare the measured impedance ZF with a setting impedance, a set value. Okay. So this is the characteristics of as seen by relay. This is one of the trip characteristics. Now, Now, like in overcurrent relay, we have time versus current, right? This is, sorry, time versus current in IDMT characteristics, right? And we have instantaneous, we count this. Now, here we have an impedance, so the characteristic is not, the trip characteristic is like this for impedance character. So it has a setting. This is the setting, our setting. So this is the setting, Z set. The reach beyond which I will declare there's a false. Okay. You know, the reach. This is the setting I want to find. So it's like this is an impedance. It's a circle centered at the relay location. So when a fault occurs inside here, inside the circle, the relay declare that there is a fault in the line. Okay. And if the fault outside here or anywhere, the relay will be stable, will not declare that there is a fault. Okay, will not operate. So relay in general, now I will go over the strip characteristics, different types of strip characteristics. Now to implement this, we can use a balance beam to compare two signals. The first signal, which represent our setting, which is the setting, this is Z set. So we know that the trip action really operates. We say it really operates if Z measured, which by the relay, is less than Z setting. So the trip action that I want to have Z, I'll write it here. I want to have if Z setting, Z measured by relay, which is ZF, is less than Z setting, relay operate. And now Z setting, this one, if I multiply both sides by I, so I ZF, okay, I multiply by I, both sides, so this is less than or equal, okay, so less than or equal Z setting times I also. And if I take this one, if I take that one this time to other side, so it will be Z setting I minus, okay, I ZF should be greater or equal 0 for the relay to operate. Now we can, this voltage Z setting times I minus I times Z fault. When you multiply I is I fault, I'll call this I fault so that so when you multiply I fault by Z fault, give you the voltage at this, at the V fault. Okay, so this is VF should be greater or equal to 0. And or not, and also I can say also this is one Z setting, or instead of bringing, So we can take the difference between these two signals. If they are higher than 0, then relay operates. This is the principle. So it's like a comparison rather than I divide voltage by a current. So this is another way of I fault times I fault times R greater or equal to VF. Okay, then I want to operate trip. So this is the trip, okay, action. And this is called, the left-hand side is called operating quantity. And the right-hand side, restraint quantity. Because as this increases, it will restrain this from operation. Restraint quantity. So we have two signals, S1 compared with or equal to S2 for relay operating. So I can use a balance beam to compare these two. Now on the restraint side, I want the relay not to operate. So I'll voltage from VT directly going to this coil. Okay, and in the operating quantity, I will operating quantity. I will use. I will take the current from the CT. I'll multiply it by a setting. So I'll put here, let's say, impedance. Okay, the setting. And now that current times this impedance will give me the voltage proportional across this coil, and that's called the operating coil, and this is this restraint coil. And that quantity, when IZ setting greater than VF, which is here, this force, will have a force here, and I have a force here. So if this force is greater than this, this beam will be like this, okay, and this contact will be tripped. So this is called comparison, a magnitude comparison. I compare the magnitude of this quantity, a magnitude of this, with the magnitude of this, and that gives me a circular action. So this is IZ times this is this value, the magnitude of the circle. This is my setting, and the magnitude of VF can be anywhere. It could be here, could be here, could be here, okay, which is I times Z faults. It could be this side, it could be that side. And if you compare this magnitude of this with the magnitude of IZ setting, it will give me, right, the, if you compare this magnitude with this, I will be able to know if the fault inside or outside, and I would like to know if the relay trips or not. So in a state of division, we can use comparison. So this is how it can be implemented. So again, on distance protections here, I have a relay that requires a voltage and a current, and it measures the impedance either by comparison or by division. Like in this case, VR over I give the measured impedance, fault from the relay location to the fault point. This is, I called it in the previous slide as ZF. I called it as V relay, relay measured impedance. Now fault, now relay ideally, the line impedance is fairly proportional with the line length. Okay. So at end of the line, this is ZL. At middle of the line will be half of that impedance. So if the fault occurs at the in the line, so the measured impedance will be less than a Z setting, and relay takes action to clear the fault. So normally Z setting that we would use is less than Z line. We take normally 80 to 90% of line as our setting. Of Z line as our setting. And why we cannot take 100% that our setting, that instead of comparing the measured impedance ZR with Z line fully, why don't we use the full line 100% Z line? If any of the measured impedance less than Z line, I relay inside, and that's because there are some errors in the VTs, CTs. Okay, in the CT we have 5% error. So if I have here the impedance of the current measured have 5% extra or 5% less, the impedance will be 5% higher or 5% lower, even more, because this is 1.15, 1 over 1.1 times 1.05 or 1 times 0.95. So that really 1 divided 0.95, which is 5% lower, will give us almost 5% higher in measured impedance. And to take this, so I cannot have what means 5% higher of the fault. Even here inside, we'll see it as a little bit outside, okay, because it's measured higher impedance. And to overcome this, or if it is we reduce this reach, okay, to by 10%, it depends on the error. The CT errors depends on the measurements of error also. A relay has also, it's not accurate 100%, okay, it has measurement accuracy error. The line impedance that we will use, okay, are they based on measurements or based on calculation? As you have covered in Power Systems 1, you find the line impedances, okay, from the R, L, and C, and these calculated might not be exactly as the actual value, because actual value are affected by temperature, by so many factors. So these parameters also might have some tolerance of the line impedance. So as a result, we don't set relay at 100% of the line. We take a 10% at least to 15% margin. And how then the relay measure the line impedance? So it will take Z line, how the relay sees this Z line. I have to refer this line to the relay side and see how they. Suppose now, if I divide this two quantity V at the secondary side of the VT and the current at the secondary side of the CT, and I know that VR is equal to V at the bus, okay, which is V, I'll call this VF, for example, okay, divided by the VT ratio, give me VR. And similarly, this current, I fault, okay, this is the voltage at the bus, at the relay connection of the VT during fault, VF, and this current will be I fault over CT ratio, give me IR. So if we rearrange this, will be VF over IF times CT ratio over VT ratio, and VF over IF, you divide this over this, it gives me the ZF, okay? So the relay, ZF, which is the impedance at the primary, at the line from here to the fault point, the relay will not see it as ZF in ohm. Maybe this is 10 ohm. It will not see it at 10 ohm. It will see it at 10 ohm times the CT ratio over the CT ratio. I have to take this factor into account. If I want to transfer any parameter from the primary side of the okay to the relay side, an impedance now, I have to multiply it by CT ratio over VT ratio factor. An example, now a line that has 4 plus J30 ohm, positive sequence, for example, impedance, and I have a CT ratio and VT ratio of this. Now, the impedance transformation ratio is CT over CT ratio over VT ratio. Now CT ratio 500 over 5, which is 100, and the VT ratio is 20,000 divided 115 is this value. Yeah, this is called the transformation ratio of the impedances. Now, this line impedance will be seen by this relay as Z line times transformation factor. So it will see it as 2.3 plus 17.25 reactance. Instead of 4 ohm, it will see it as 2.3, and the 30 ohm, it will see it as 17.25. And once we transfer it, then we can take 80% of this as our setting. Okay, this is our setting. So generally, our this is called our zone 1 setting, which is represent 80% of the line impedance, and this zone acts instantaneously whenever an impedance measured by relay less than 80% of the line impedance. There are different types of characteristics that is used in trip characteristic used in distance relays. One of them is the impedance characteristic. We have more, this impedance characteristic is a circle, it centers at here, the 0 point. This is Rx plane or XR plane. And more characteristic is a circle, but it's it crosses 0, okay, here. So it is offset from 0. So this is a center, and this is our setting. This is Z setting. And now in this case, this is our Z setting. This is Z setting, which is Zn here, is Z setting. Okay. Now this is called offset mode. This is offset mode. It's also a circle, but it is offset a little bit from 0. We have lenticular, like lens. We have relateral. We have polygon in general. Okay. So why we have different types of characteristics? Each have advantages and disadvantages. Okay. So I'll go for the impedance characteristics. Impedance characteristics, it cannot be used because it doesn't differentiate forward or backward. The force backward, let's see. Here, if this is the relay location. This is the line impedance, for example. Now, fault forward is somewhere here, but fault backward behind the line, it also operates. So this is non-directional. So it cannot be used without a directional unit. The advantages of MO, however, there is advantage of this, that it gives you good resistive coverage of fault at here, at the middle of the line. I can have up to this fault resistance. Still, it can detect this as internal faults. While in MO, it is inherently directional. I don't have to have a directional unit with it. Okay, and so I need to have two settings for MO. One is the characteristic angle, or the angle settings, which represents this and this the second one is the setting of its reach setting, which is this value. This is our Z setting. Okay. So the fault inside the small area, the relay operates. If outside, it restrains. This is so advantage here. I don't have to use a directional unit. And offset mode is used normally as a backup. If I have a line and I have distance relay here 21, and if a fault's here, I want a fault in the bus, I want to, or behind the bus, I want to have to a sort of backup backside. This can be also detected by this. Or so it's used only to make sure that all faults within even here close to the bus, it can be detected also by this. So it's used as a backup operations. We have also the quadrilateral or polygon type. If you compare now the quadrilateral characteristics, this is the or polygon, which is yellow area. The advantage now, this is I will draw the more characteristic also with the blue line. So the more is this is the more characteristics. The red is the offset mode. Okay, the yellow area is the quadrilateral or the lenticular. Sorry, the polygon type. As you can see, if I use more, this is the resistive coverage. Okay. If the fault here, but the resistance, fault resistance larger than this value, more will not see these faults as internal faults. Now, if I use impedance characteristics, now this will become a circle. Its center at here, and now this will have more resistive coverage up to as compared to offset mode or mode. However, I need to have a directional unit with it, so it only acts at the upper side. Okay. Now, the advantage with this, I can increase the resistance cover in the polygon type. I can increase this line up to here so that I can detect more fault resistance. So I can go up to this point. When the fault resistance here, still the relay see it as internal faults. Up to a level where I don't want to relay also detects line load impedance as a fault. So you have to be careful to the extent of this line. It has to be okay before the load area. Okay, this is Z load impedance. Okay, so if the trip area extended to the Z load, we call this load encroachment. So the load becomes inside the trip and the relay will trip even during normal loading operating condition. So we have to be careful to the extent of extending this line to the load area. Shouldn't be, I have to have a margin. So in this case, I have to have this resistance as a setting. Okay, and also I need to have this reactance X as a setting, okay, which is this line. And lenticular, also I can have this this line as a setting, directional unit as a setting. This line also I have to have, where is this value? It crosses here. So I need to have this setting. I need to know this angle, also this another setting. This angle also as another setting. So these are the settings when you want to set quadrilateral characteristics. Lenticular, it is a combination of two more. If you combine these two more characteristics, and this is more or offset more, sorry, you end up with this overlap region. So why we go for this? There are the problems with load encroachment. When you go for zones, if you extend this to zone 2, which covers more area, the tendency to go to load is more, okay? And that's why they want limited zone 3 to with using 2. To implement this in electromechanical relay, they used to have two relays combined together to get this. With numerical relay, it's easy to do this, and you know, with just an equations. This is how can we adjust the aspect ratio where I can make it closer to each other or further, so that I can overcome the load encroachment. This is the load area. I can, with this, I now have solved. The load will not be inside the trip area. Okay. In order to protect a line, we need at least two zones of protection. Okay, one zone 1, which covers 80 to 90% of the line, and this zone is instantaneous. There is no time delay. And zone 2, it covers the remaining 20 that it is not covered by zone 1. But however, it has to be time delay because we don't know if the fault at the end of the line or at the beginning of the next line. The third zone, so zone 1 and zone 2 protect the line itself, the protected line. But zone 3 as a backup. This is used as a backup to the remote or to the remote adjacent line. Okay, and it has also to be delayed because we want to allow the adjacent line primary protection to act first, and if they fail, then zone 3 of this relay will take action. Now, if we plot the lines here, line AB, okay, this is one line BC, another line C, whatever. This is a third line. Each of these lines for transmission line, we need to have a distance relay at each end of the line. So have relay A at the beginning of the transmission line and relay B at the end of the transmission line. So relay A look forward in this direction, so it has zone 1, which covers up to 80% of line AB. Okay, and zone 2 of relay A at A, it covers 120% of line AB, so it covers up to here. So it covers at 20% more than line impedance. And zone 3, okay, it covers the next adjacent line. So to provide a backup, cover the next line, so up to here. So it fully covers the next line. So that's as a backup. So relay A now acts with zone 3 as a backup protection for any fault in the adjacent line. Similarly, relay at the end of the line trying to protect the same line with zone 1, which cover 80%, zone 2, which covers 120%, and also could be zone 3 that covers if you have a line here. Okay. So what are the settings? Settings, as I mentioned, for zone 1, 80% of line protected. Suppose I'm talking about line AB, this line. Okay. So I have to set it at 80% to 90% of ZAB, zone 2, 120% of the line impedance, zone 3 forward, 120% of ZAB plus ZCD in this case. Or sometimes we can also write this, or we can also use 100%, I would say 100% to 120% of ZAB velocity, or sometimes we say ZAB plus 120% of ZCD. This is also a valid setting. Okay, or say or. If we look these zones, A, B, so this is point A and this is B, C, D. Okay. Now, if we look, zone 1, zone 1 covers up to 80% of the line AB. Zone 2, if I am using more characteristic now. Zone 2, the green one, it covers up to 120%. Zone 3, which is the gray color circle, I use offset mode. This is offset mode. So it covers up to 120%. It covers this line plus a margin so that I make sure that all fault in this line CD is detected. So it provides a backup to faults for the protection of CD line. And it's offset mode so that I make sure that I detect also faults backside this line. Okay. So this is the offset mode. So what are these settings? Setting zone 1 is setting to protect the 80 to 90%, and the time setting of this is instantaneous. There is no time setting. It's almost there is no time settings. So it's set at minimum time. So the remaining 10 to 20% is a security margin to account for CT and VT errors. Zone 2 is set at 120% of the protected line. It is time delayed by 0.3 to 4 seconds, and is provided to protect the line so that we have 100% now of the line is protected when you provide these two zones. And it is it should not reach beyond 50% of the adjacent line. If you go beyond the adjacent, next I will show later, you need to do also a problem of coordination between zone 2 and another zone 2. Zone 3, which is optional. Now these two must use to protect the line. Zone 3 should cover the protected line plus the longest adjacent line. Okay. I'll take 120% to 110 to 120% of the summation of the impedance of the line plus the longest adjacent line. And it's delayed by twice the time, this is the coordination time interval. Okay, it's twice this, so we can use from 0.6 to 1 second delay. And to provide backup for the adjacent line. So this is the zone 1. It covers up to 80% of the line, and it's instantaneous. Zone 2, it covers 120% of the line, but time delayed. And zone 3, it covers zone 3, which is not shown here. It covers all of this area. And as a result, if the fault falls inside the yellow area, the relay trips instantaneously. If the force happens in the blue area, okay, include, of course, the blue circles includes this. It will take time to delay, which is 0.3 to 0.4 second delay. Then it trips the circuit breaker. Of course, here in this area of zone 3, it delayed by 0.6 seconds and then trips. And we have to have a condition, especially zone 3. Zone 3, it has to be not reaching the zone area. If the load impedance, Z load, becomes inside this, it will lead to distance relay to maloperate. And And this one, now this is same. The green area represents zone 1 coverage area. If a fault happen here, relay 21 trips instantaneously here. And the blue one represents the reach or the zone of the zone 2. Okay. So when a fault happens at the end of the line, this is, we said this is up to 80 to 90% of the line represent. Now what happens if fault happens at the end 20% of the line? Then this relay will not trip instantaneously, but trips after a time delay of 0.3 seconds. 0.3 to 4.4 seconds, depends our settings. And trips. Why it doesn't? Because it's not sure if the fault is here or here. If it is here, it will allow the next line protection to act first. So the fault here in this, still in zone 2, okay, but it's in the next, at the beginning of the next line. So this relay will trip first zone 1. This is zone 1. Zone 1 of relay of breaker 3. This is zone 1, okay, of relay at breaker 1. So because this is falls in breaker distance relay at breaker 3 in zone 1, which is instantaneous, it will trip instantaneously to open this breaker. Once, although this has also seen this fault within its reach of zone 2, this is zone 2, but it will not operate instantly. It will wait 0.3 seconds. So before 0.3 seconds reached, this has already tripped and the fault is clear, so this relay will not operate. And that's required. This would, this 0.3 to 0.4 second delay in zone 2 to allow coordination between relay at breaker 1 and relay at breaker 3. Now, how do our relay measure the impedance? It measures it using how the relay 21 distance relay measure the fault impedance correctly. We want to measure the positive sequence impedance correctly for different types of faults. The impedance relay implements these measuring units, 6 measurement units. For 8 ground faults, the positive sequence impedance measured by dividing the phase voltage of phase voltage, or this is for each, and now I'm talking about phase A unit, phase B unit, and phase C. Sorry, this is B to ground faults. This is C to ground faults. Okay. Now for A to ground fault, it takes phase A voltage over IA current plus a constant times a compensation constant times 0 sequence current. Compensation constant is the Z line 0 sequence impedance of the line minus positive sequence impedance of the protected line over 3 times Z line positive sequence impedance. And I0 is the summation of the 3. And or sometimes if this is 3 here, the constants here will be without 3. Just to reduce computation, we just summation here without multiplication, because this is just is evaluated, one time, and it sits inside the relay. While this relay always computes summations at each instant in time and check whether impedance has fall below its measure Z1 and check it with zone 1 reach. If it's fall within zone 1, then it declares A to ground false. Okay, and as for B to ground false, C to ground false, and for AB or ABC, AB to ground false, they use the difference in voltage, in phase voltage, between A or B, if it is AB fault, over the difference in currents. That will measure the positive sequence impedance. And similarly for BC fault and CA fault. So we have 6 measuring units in order to measure correctly the fault impedance from the relay location to the fault. And which impedance what we are measuring is the positive sequence impedance of the line. And then we compare. So what the relay does, the first step is to detect that there is a fault. Then it has to know what type of fault is this. A third, it will use the correct measuring unit based on the type of fault. It will use this one of the three or the correct measurement units to measure the fault impedance, and then it will compare it with the zone settings, okay, and then takes action if the fault inside the one of these zones, okay. And inshallah, stop here. In the next class, I will explain, cover some examples, okay, and with that lecture, I'll finish this chapter, inshallah. All right. There is a proof for the yes. Do you have any questions? Okay. I'll stop recording.